There we go. All right, so welcome. Hope you're all doing well. Today we're going to finish up Unit 8. We have one more topic. It is on buffer capacity. Really nothing too different, just kind of things to think about in terms of how buffers work and what makes them useful and when they're less useful, more or less. So my plan then tomorrow is to have an in-class review. Like every single unit in this class, you have 2 review sheets, an in-class review and a other review. And you are kind of expected to try both, use both as your studying tools, and use my outline on the topics, like the first page of that review sheet. The non-in-class review sheet is always a breakdown of topics. There's an extra sheet at the back end of this unit, which is called the helpful tips on buffers and indicators and titration sheet. That's just kind of a bulleted list of like, hey, what scenario do you have? This is what you should use. Because one of the biggest problems in this unit specifically is, once we get done with buffers, you kind of forgot what the heck we were up to in 8.2 and 8.3. And then you start trying to use the Henderson-Hasselbalch equation for everything because it's nice and easy, but it doesn't work for everything. What does the Henderson-Hasselbalch equation work for? That's it. That is literally it. If you don't have a buffer, that equation we used yesterday, pH equals pKa plus the log of conjugate base over acid, if you don't have a buffer, that thing doesn't serve a purpose. It's really nice when we do have a buffer. Makes life easy. But if we don't have a buffer, then we've got to kind of go back to the old ice table stuff usually. Okay? So that helpful tip sheet it's got a whole breakdown of all different scenarios, all the things you can expect to run into, and basically it helps you pick what you need to use, so to speak, right? Hey, if you got this, please use that, kind of a thing. So it's kind of like flow charty without the flow chart, I guess you could say. All right, so without further ado, I guess, let's jump into 8.10. Buffers are made so that when either a strong acid or strong base are added, the buffer can neutralize either, and maintain a pH close to that of the original buffer. Calculate how many grams of sodium acetate I need to create a buffer with a pH of 3.74 using 1 liter of 0.4 molar acetic acid. This is basically the same problem I gave you yesterday with different numbers. Yesterday, we solved for how many grams of sodium acetate we needed for a different buffer. Today, I'm asking you to do the same thing, same substances, just different numbers. Okay? If I want to solve for how many grams of salt I'm supposed to add to my buffer, given the information I have, what do I probably want to start with? What should I start doing here to figure this out? Any ideas? And if you look at yesterday's sheet of this exact same problem, you can kind of trace through what we did. We should start with the liters eventually to use factor label. Do I have a molarity of my base? No, I don't. So tracing back even further, we got to do the thingy to get the molarity. What's the thingy? No, not this time.
Are you trying to find the molarity of base?
Yeah. Well, I'm sorry. I want the molarity of my conjugate base, not of my. Like, we're not adding a strong base, right? The hard part with doing it that way would totally work if I want to get like the total molarity of OH, of hydroxide. Mm-hmm. But that's not what I want in this instance. I want the molarity of my conjugate base so I can use that in the factor label to solve for like grams of something. It does. What's the famous equation from yesterday? Yeah. That's the one.
Oh, I don't think he'd like that.
I knew it was coming. I'm like,
It's only the hassle. You
I
shouldn't even
can't-
send it.
I know, I'm sorry.
Then-
well, normally, normally it kind of like comes up naturally as, somebody thinks it's funny and then it sticks. So I figured I'd streamline the process.
So it's just Hasselhoff.
Henderson Hasselbach, yes.
Oh, so I gotta say both H's?
Yeah, or just call it the HH equation, that's fine.
Ooh.
I'm partial to the HH. Okay, what do we know?
We know the pH,
Yep, what's the pH?
3.74.
We know the pKa.
No.
I didn't give it to you. There's a reason why I didn't give it to you, because we used it like 3 times yesterday. Oh, I mean, yeah. Ka of acetic acid equals 1.8 times 10 to the negative fifth. If you take the negative log of that, you're going to solve for pKa.
Oh, is this the 4.75?
Yeah.
Oh.
And again, we used that a whole bunch yesterday. That's why I didn't. On a test, I have to give you that, right? I have to. I have to give you something to obviously solve for that. So don't freak out if it's a test or if it's the AP test. They're going to give you a K value because otherwise you can't possibly solve it. So 3.74 equals 4.745 plus the log of base over acid. Base I don't know. That's the end goal of this process. Acid I do know. What's my molarity of acid? 0.4. Okay. I'll subtract this. Take 10 to the power of both sides. And then eventually I will have my molarity of base. Have you done that? Okay, go ahead. I'm assuming you can do that algebra, I hope.
Negative 1.2.
Okay, I'm showing intermediate steps. You don't have to show intermediate steps, but some people obviously prefer to see it this way or to write it this way just to make sure they're not skipping things or screwing things up. Oops.
What do you do when you're a little 10-carat thing?
It's raising it to the 10th power.
10 to the power of this,
Oh.
10 to the power of that. So then what happens over here, right? That's how we get rid of that log. That's the whole idea. When you take 10 to the power of a log, these just go away, and what you're left with is what's inside the parentheses. So then I get 10 to that equals A1 minus over 0.4. If I multiply this by 0.4, I'm getting a molarity of A, or the conjugate base, I should say, equal to 0.395, 0.0395, I should say, sorry. There's a second on that? All right, good. So now what should I do? Math.
I like that. Purple.
I'm a fan. I like to go purple and orange usually when we got these more fun boards. I think I can change on the other ones too, but
I like purple and orange.
Mr. Brosnan, what's your favorite color?
purple. I love purple. Really? Great color.
Purple is my favorite color.
Why is it?
It's just, I don't know. I like
I
it.
feel like it's kind of underrated.
It is underrated. I like purple.
It's like one of
It's a
the
good
wearing
color.
I support them.
I've never seen you wear purple once.
That's a lie.
Mine is kind of purple.
Dude, that is blue.
That's a lie, though. I have purple
Some
shirts.
is
Said that.
I haven't seen it.
on the board.
I have purple shirts.
Oh.
Wear one tomorrow.
Okay, fine. I'll wear a purple shirt tomorrow.
If you don't, I'm gonna be very mad.
Well, we can fight about that.
Okay.
What are you solving for again?
Yeah, that's a great question. What are we solving for again?
Grams of sodium acetate.
Okay.
Oh,
So now I know the molarity of it, right? Okay, yeah. Now we're on the factor label.
Molarity is like such a bad way to start.
It is. If only we had a volume. Oh,
Look at that.
we are lucky.
What if that was like a bad volume though?
Meaning, what's a bad volume?
I don't know. Just say bad volume.
Like
Like
1.7.
That'd be fine.
Fine.
Doesn't matter. We just use it in factor label. The times when like the volume gets annoying is when we go from like a mine table to an ice table, right?
Oh, okay.
Because then we have to convert our moles back into a molarity. So then if we have some obscure volume, we have to like obviously acknowledge it and divide by the appropriate volume. If the volume is 1 when you go from a mine table to an ice table, that's nice because then you don't have to even care. It's just obviously the number stays the same. But anyway, so we have a liter, and I have this molarity, and this is moles of conjugate base. I'm going to write that as A1 minus, but in reality it's acetate, right? Because this is specific to the specific buffer that we're working on. And that's over 1 liter. And then I'm going to go from moles of my conjugate base into grams of my conjugate base, which is technically sodium acetate. Again, more affectionately known as nacho.
Not sure.
The molar mass of nacho is 82.034. And again, we calculated that yesterday, so I'm just kind of streamlining the process today. And when it's all said and done, how many grams of nacho do we need? Did you say 4?
Yeah. That's like gas, right? A lot more.
Yeah, and by a lot more than 4, he means less than 4.
Yeah, this is 3.24.
I'm glad Mr. Brazza understands.
Let's translate.
Yep.
I was actually pretty close. Of all the numbers in the world, I was pretty close.
You were really close. I mean, if it was Price is Right, though, you're eliminated, so. Anyway, so this is the process for solving for the mass of salt. And when I say salt, what I care about in that salt is my conjugate, right? The salt is how I get the conjugate base in my buffer. Because what do you need for a buffer?
You need a weak acid.
We need weak acid and conjugate base. So I have the weak acid, it's just the solution. I've got 1 liter of 0.4 molar acetic acid. But how do I get my conjugate base in that solution? I add some salt that contains it. So to solve for the mass of how much I need, I used the Henderson-Hasselbalch equation to get the correct molarity of base. Once I know how much molarity of base I need, I can then use the volume of my buffer, the molarity of my base, the mass of my base, or the molar mass of my salt, I should say, to get to the total mass that I need to add. So if I had 1 liter of 0.4 molar acetic acid, and I added 3.24 grams of sodium acetate to that and stirred it up and dissolved it, I would have a buffer at a pH of 3.74. Okay? Try the next one all by yourself. Same thing, more or less.
Was it only when the numerator is good with the denominator? Is that when the math is really ugly and you don't have to know?
No, what we were doing at the end of the class yesterday was trying to create a buffer by neutralizing weak acid with a strong base. So we have a problem on this sheet that's kind of the same context, just with a better set of numbers to launch from. Yeah. It won't happen again, and we won't go back to that.
So like that number can be bigger and it will cause me problems?
Correct. Yes. In this context, yeah, it's going to be no issue. Question, Emerson?
No, I think it's fine.
Oh, okay. Sleepy today?
Oh, that's like. This is hard.
If only there were a solution for that.
It's basically from that, I almost got the answer. long as I have it set up right.
Yep.
Yes. Super hot. That's all. Anybody else? You're fine.
Pretty comfortable.
Really? Yeah, that's
I think there's been a draft coming through the door. So it's nice in here.
Emerson, are you comfortable? Can hear your pinky.
You can? That's fine.
I think if you can hear it, then I can probably hear it. Oh, yeah. It's like, it's external. Your finger's probably on the
Hey, are you trying this problem?
Yeah, I think I'm doing pretty good. It seems to be going well.
I mean, it is the same setup as the last one.
Well, I know. I'm just making sure you guys are doing stuff.
Wow, that was kind of mean, Jager.
You're just the one over here, plus the same setup. Go straight somewhere.
Okay.
Those eggs that you need?
Really?
Those eggs that you need? I was talking
You made eggs last night?
Yeah.
I made eggs last night.
Oh,
I made eggs this morning.
I made eggs for a speech that I should have been recording. Then I recorded it. So
Fun.
I forgot to press record. And I was very mad. What did he say?
He said yes.
Really?
Probably just doesn't know how to handle it.
Kind of mean.
Mr. Robbins.
That's it for this one, right? I didn't ask for the mass of this one. Benton?
I'm, probably a bad question, but you're trying to find the concentration of acid. So now I think you're trying to.
Oh, my bad. Right?
I'm so confused.
Sorry, I went on autopilot.
I was just gonna say, how do you put that in?
Sorry.
Okay, that makes sense.
Yeah, so I just went on autopilot. I assumed we had the acid still. We don't have the acid still, my bad. So we have 0.5 molar of the base. Let's fix this.
Should draw a line.
Thank you for stopping me. Let's try this again.
Writing brackets is probably the hardest.
I hate that. The brackets are so.
I'm so bad at them. Yes, exactly. I always get stiff by parentheses.
How's that? Is that better? Okay, thank you. I didn't show that other intermediate stuff, right? But what I'd have here is obviously I'd have some numerical value over here equals 0.5 over HA. Then I obviously want to move HA over to this side and then divide both sides by whatever that numerical value is. So I end up with like 0.5 divided by 9.8855, blah, blah, blah. Okay. So there's my molarity of acid in this buffer. Now, a couple things of note. I have 0.5 molar conjugate base. I have 0.05 molar acid. I have 0.4 molar acid in this buffer and 0.04 molar base. What's the ratio of acid to base or base to acid in these two buffers?
It's like
1 to 10, 10 to 1, depending upon which one we're looking at and which how we're describing it, right? So it's a 10-to-1 ratio or a 1-to-10 ratio. Okay, keep that in mind. Are either of the buffers that I've created in problem 1 or 2 what we would consider good buffers? In other words, if I add 0.1 moles of HCl to the buffer in problem 1, what's going to be the resulting pH? Let's do it. I'm adding strong acid. How do I represent strong acid in a chemical reaction? H1 plus. And what's the base of my buffer? Because my base of my buffer is going to neutralize that stuff, right? So what's the base in my buffer? What's the acid in my buffer? No. That's the acid. What's the base? The conjugate base of my acid, right? So it's acetate. So I have H1 plus acetate. And these are going to react. That's what we're looking at right now, right? My question is I'm going to add some acid to my buffer. What's the pH going to be after I add the acid to my buffer? Okay, so we do this, and when that happens, I'm just going to end up getting the other piece of my buffer, I guess you could say. And when I have an acid and a base reacting with one another, what kind of table am I setting up? If I have an acid and a base reacting with one another, what kind of table am I setting up? Mine or ice? Mine. Mine tables are for neutralization. Mine tables are for acid-base reactions. Mine tables are to figure out how much of the acid and the base are reacting with one another. Okay? So this is a mine table. Now, fear not, we're not going to go crazy with this. It'll be pretty simple. How much acid am I adding? 0.1 moles. How much base was in my first buffer, this one? 0.0395 moles per every liter. How much did I have? A liter. So I have that many moles, right? 0.0395. How much of this did I have? I think I had what, 0.4 of the acid, the weak acid? Maybe? Yes? Okay, acid-base reaction. What's going to happen? You're going to react until something runs out. Acids and bases neutralize until something is gone. What's going to run out? Probably that. And what am I left with when it's all done? Oops. I don't want to think. Thank you. I can do that one. Hey, I can even do this one. We'll keep them all. Okay, neutralization is done. What do I have? What do I have right now? Do I have a buffer? No. I don't have a buffer, do I? What do I got? 2 acids. That's strong. That's weak. We have broken the buffer. It's not a buffer anymore. What I have is strong acid and weak acid. I want to solve for the pH of this stuff. How do I solve for the pH if I have strong acid and weak acid at the same time? Use the strong. Now, in reality, the weak acid, in theory, is going to supply some H1+. But for our class, for our purposes, we're not really ever going to acknowledge it. if you have some strong substance, let's just focus in on that. So this is moles, because it's a mine table, but we had 1 liter of stuff, right? So in reality, I have a molarity of H1 plus equal to 0.0605 mole. Again, this is moles, but we have 1 liter, so I just have to, so, you know, I divide it by 1 and it's the same. How do I solve for pH? Let's take the negative log of that molarity. What do we get for a value of pH here? How did our buffer do at resisting pH? Well, our buffer broke, so it didn't do very good. Okay, let's try the next one. I'll leave this up for a second. Try the next one. That says, hey, what if I add 0.1 moles of base to the buffer in problem 2? Same kind of thinking. Obviously, we're adding different stuff going in the opposite direction, but the setup is similar. Okay, try the next one, please. What are we setting up? A mine table. What's my reaction going to be? Uh-huh. And what inside the buffer is going to react with the NaOH? The acid of my buffer. What's the acid of my buffer?
Sodium acetate.
What's the acid of my buffer? Acetic acid.
Oh, so close.
That's why I kept asking more questions. I was making sure that underlying, you know, underneath it all, we were arriving at the same place. Evidently, we weren't. When I add base to buffer, it's the acid in the buffer that will neutralize it, right? NaOH, strong or weak?
Strong.
How do I write it?
Or OH.
OH1 minus. Do I care about the sodium?
No.
Nope. It's not useless, but in this context, it's kind of useless. In other contexts, it can serve a purpose.
Like what?
Well, it depends if you wanted to do, I don't know, there's redox reactions that would involve sodium. If we boil up all the water, then all of our ions would come back together, make salts. It's not what we're up to. So for this purpose, it's useless. What do I get as products?
Like water.
Mm-hmm. How much of the acid did I have from problem number 2?
Yeah, 0.6. 0.6.
Thank you. How much of the base did I add? How much of the conjugate base did I have in my buffer? I think it's 0.5, wasn't it, for the second one?
Yes. Where's that from?
Problem number 2.
Yeah, it's the top number, right?
What?
Yes, correct.
Oh, I think I got it.
Acid, base, what happens? Yep, until something's gone.
H2, C2, H3.
Okay, neutralization is over. What am I left with? What are these two substances? Strong base, weak base. So if I want to solve for the pH of this, we'll just acknowledge the strong one. Now, in reality, does that weak base provide more hydroxide to our solution? It does. But we're going to assume it's negligible. In this instance, it actually probably isn't negligible because we have like a 10-to-1 ratio here of weak to strong. But again, in this class, it's just not necessary. What we'd have to do to legitimately solve for the true full molarity of hydroxide is we'd take this value, we'd set up an ice table for this value, solve for X, and then we'd add X to this to get the total. It's totally fine. Like, again, within what we've accomplished so far in this unit, you guys could do that. It's just not something that AP tests on, so whatever. But anyway, this is my moles of hydroxide. In theory, we're going from a mine table, and I would need to convert that to molarity. But once again, 1 liter. So my molarity of hydroxide equals this. How do I solve for pH? Well, let me take the POH first. What do you get for a POH? And if I take 14 minus that to get the pH, what do I get? Is there a second on that at all, or anyone else get there too? Thanks, Jacob. 695. So this was 1.305.
I didn't.
Oh.
Wow, there's lots of just disagreement.
1.5.
Did you round anything along the way, Jacob?
No, I just put -1 0.0484.
Oh,
0.
Oh, I thought that was a tiny 8.
What?
Well, I thought he just, you know how it's ugly.
oh!
I thought it was like a really sloppy 8.
What's that I hear?
Caught himself.
So what should it be? Sorry. 0.6? Which means this is. Okay, cool. Yeah, I mean, it's all close, right? So, okay, did our buffer do a good job? No, it failed miserably. Why? Well, we broke it again, didn't we?
Yeah.
The buffer has broken. Buffers, yes.
So for these problems, you're giving us the 1 liter, so you don't have to worry about converting them on the test. Are you gonna do the same thing?
Probably.
Probably.
I said probably.
Does that mean that you're
That's
just
just
gonna
get
cite
melee
what
again on
wasn't
the exam.
Just say melee?
Well, yeah, because last test we were supposed to.
Okay,
we were like,
okay,
oh, this is
okay.
like an easy exam.
Just give us a yes or
And then
no.
everybody needed
I
to
will
test
not,
it.
I will not give you a volume other than 1 liter for the upcoming exam.
That's on record right there.
On record.
Will that be people?
I doubt it.
Those people are.
I doubt it. Can't guarantee that. But yeah, they tend to be nice with that situation as well. Anyway, so here's the deal. We made a buffer in problem 1, and we broke it in problem 3. We made a buffer in problem 2, and we broke it in problem 4. Were either of the buffers that we created in 1 and 2 good buffers?
No,
No. How much acid and base did I add to break them?
not that much.
0.1 moles. That's not a lot. I mean, they're really like, it should be able to withstand that, shouldn't it? So here's the moral here of the story. Here's the conclusion, okay? Buffers have a range in which they are effective. The closer the pH is to the pKa, the better buffer you're going to have. I said this yesterday. Kind of got a little ahead of myself, okay? The range of pH for a buffer that would be considered appropriate is given as plus or minus 1 away from the pKa. Now, we were within that range, actually. We were at the extremes. What was our pKa of acetic acid? 4.74. We made a buffer at 3.74, we made a buffer at 5.74. So we took the extremes of that range. And what we figured out was that it's not that good. Okay? So again, what's the whole idea behind this, or what am I trying to get at? What I'm trying to get at is buffers are best when they are close to their pKa. The further you get away from an acid's pKa value and try to make a buffer with it, the more useless it's going to be. If we make an acetic acid buffer at 4.74, it's probably going to be a pretty darn good buffer, and it's going to be able to withstand greater quantities of acid or base in that process. If the buffer you have created is easily broken, what can you do to increase the capacity of that buffer? Okay. We broke 2 buffers in problems 3 and 4. What could I have done to make that still work, so to speak, or still exist? Let's just add more stuff. Meaning, like, if our buffer has more acid and more base in it, higher molarities, well, then it's going to be better. For example, if I'm right here, if I'm going to add 0.1 moles of weak acid, or strong acid, I'm sorry, if this molarity was bigger than that molarity, well, then my buffer wouldn't have broken, and it still would have done its job. Right? So how do you make a buffer have greater capacity? You increase the moles of weak acid and conjugate base. If you increase the moles of both of those things, now it can withstand larger quantities being introduced. The higher the concentration of your buffer, the more acid or base it can neutralize. That makes perfect sense, right? That's pretty logical. So the effectiveness or the usefulness of buffers really is dependent upon 2 factors. Number one, you want it close to the pKa, because when it's close to the pKa, the ratio of weak acid and conjugate base is pretty close to 1 to 1. It's not perfect, but it's close. The other thing that's really useful is, if you want your buffer to be better, crank up the moles. If I have more of weak acid and conjugate base in my buffer, well, then it's going to be able to neutralize more, and it's going to be more effective. It's going to work better. It's going to last longer. It's going to be harder to break. Make sense? Let's write that out. So what can we do to increase the capacity? Increase makes perfect sense, I think. Very intuitive. Now, if we had a basic buffer, right? Let's say we made a buffer with ammonia and ammonium. Same concept, right? Same thing. If I want to make a basic buffer, I still want the pH to be close to the pKa of the acid in that buffer. And if I want to make it have a greater capacity, I just increase the molarity. I would add more of both of my components of the buffer. Higher molarities of the buffer, the more it can neutralize. The acid ionization equilibrium, which is a fancy way of saying that reaction, for the weak acid HF is represented by the equation above. A student wants to create a buffer with a pH of 3.2 using 0.1 molar HF and some molarity of KF. What is the molarity of KF? What molarity of KF is necessary to create this buffer? Go for it. Let's see what you can do. If it's a buffer, what equation is in play? Yes, the Henderson-Hasselbalch equation, correct. That's what I said. You can talk to each other too. That's cool.
That's a good question.
Oh yeah, it was even nice. I didn't even give you KA. I streamlined it even further for you.
That was even nice.
Man, what a good guy.
Surprised by that.
Wait, then what would be your base? Oh, wait, we have the one. Which one? Is HF? Oh,
That's what he said.
It's pretty straightforward. Like, definitely
Yeah.
don't know.
The pH is that of an acid.
This is very. Okay, so let me go through this.
3.2.
And if you're kind of spinning your wheels a little bit, right? If you read this and you're like, well, that sounds complicated. We've done this multiple times already. Today. Okay. That's right up there, right? PKA.
That's very
And yeah. Now we just solve for A1 minus. And we're done.
That was honestly one of the next ones to do.
Yeah, I know. But when you read it, how does it sound though?
Yep.
It sounds awful when you read it, right?
Put a bunch of like unnecessary wording in it.
Oh, absolutely. This?
Yeah,
Why?
that.
Completely unnecessary.
that's
Why do you do that?
Like that entire.
That's what AP does.
AP is useless.
But then when I like
Okay,
try
no.
to get the numbers, sometimes I throw
Said
in
makes
feelings
sense.
too.
So if I subtract this, right? Right, 10 to the power of both sides. If I take 10 to the power of 0.06, and then I'll have this 1.148 blah 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 equals A1 minus divided by 0.1. So I can multiply that by 0.1. And you should get a molarity of your conjugate base equal to 0.115. Okay, so let me recap just a couple things. Couple things to think about, right? If my pH that I was trying to create my buffer at was 3.14, meaning pH and pKa are equal, what does that tell me about the relationship of weak acid and conjugate base? That they're equal. If pH and pKa are equal, then base and acid are equal in the buffer. Now, in this instance, my pH that I want to hit is slightly more basic than the pKa. So what should I totally expect from the ratio of my weak acid and conjugate base? That my base is more concentrated, right? 0.115 of the base is more concentrated than 0.1 of the acid. It all makes sense. It all should add up and kind of be logical with what we've learned. if this was a pH of 3.00, okay, and I still kept this as 0.1, well, then I should totally expect my molarity of the base to be less than 0.1, because in that case, my pH would be more acidic than the pKa of that buffer, or of that acid, I guess I should say. So all of these relationships and all of these things that we've kind of tied in over the last week are all still relevant. When I taught you about titrations last week and we were talking about the halfway point, that's leading into this. This is still the halfway point technically when this and this are equivalent. Sorry, I'm all pumped up for chem. What can the student do to increase the buffer capacity of this solution without changing the pH? I want a pH of 3.2, right? That's what we want for this buffer, apparently. What can I do to make it better or to increase the capacity? Careful. It's kind of, here's the deal. If I want to make my capacity bigger, right, I would add moles of both. HF and F1 minus, which is the conjugate base. I guess in reality it's KF, right? The potassium fluoride from that problem, which is the salt. The potassium is irrelevant, it's a spectator, it's neutral. The fluoride is what we care about. But I can't just add them all willy-nilly, can I? How do I have to add them to make sure that my pH is still 3.2? I need to maintain that ratio. In other words, for every 0.1 mole of acid I add, I need to add 0.115 moles of base. If I maintain that ratio, my pH is never going to change. Whether this is 0.1 and 0.115, or 10 and 11.5, right? Same ratio. Just way the heck more concentrated. As long as that ratio stays the same between my two components, the pH is going to be the exact same. What changes this pH of my buffer is if I start messing with that ratio and it's no longer where it was set at. So how do I increase the capacity? I add moles of both in the ratio of that, which is directly from my Henderson-Hasselbalch equation, right? I have to maintain that ratio. If I want better buffer, if I want to increase its capacity, I can totally do that. I just need to maintain that ratio to keep my pH from changing. Hopefully this is an easy question. Oh, it's a lab question. Good job, Mr. Brosnan. It's a lab question. These are the thinkiest.
I feel like you're happy about this.
Well, I am. Let's say that the student added solid potassium fluoride to the solution of hydrofluoric acid to achieve the desired molar ratio. In other words, we figured out it was 0.115 molar base to 0.1 molar acid. The student executes that in the lab. But if the bottle they used was listed as being 99% pure potassium fluoride, but instead it's actually only 90% pure, what effect would that have on our buffer? Hold on, think, don't talk. In your own head, think about that scenario. We're trying to create a buffer. We did all the paper math, we figured it all out. And we determined that we need 0.115 moles or 0.115 molar base in our buffer. So we go to a balance, we grab the potassium fluoride, we mass out perfectly what we need, we add it, and we think everything is good. But what we thought we were adding was 99% pure, only ended up being 90% pure. What's going to happen to my buffer? Or what's going to happen to the pH of my buffer? That's not nearly specific enough.
Oh, wait, which chemical is 90?
The potassium fluoride.
Okay, so basically the it would become more acidic.
Yeah.
The pH of my buffer would be,
Oh, lower.
you're correct. Why?
Because you're adding less base.
Correct. What we are adding is the salt that contains our conjugate base. If we add what we think is the correct quantity, but we realize that what we've added is not pure, that means we're introducing less base to our buffer than we thought we were, right? And if we're adding less base to our buffer than we thought we were, our true ratio is actually more acidic than what we had on paper. And as a result, the pH of the buffer would be less than, okay, the desired 3.20. That was the target, right? We did all the math on paper. That was where we wanted to hit. But our substance that we were adding wasn't pure. And as a result, the solution we got was more acidic than what we thought it should be, based on the math we did on paper. These types of questions, if you're starting to do free response, you probably have come across these. They're usually the very last one on all the free response questions, the big ones. Questions 1, 2, and 3 on the free response section of the AP Chem test. Normally, like question G is like, hey, here's a random lab scenario that messes with percentages. How does that affect your results? And it's like, oh gosh, you really have to think it through. They're tricky. So if you haven't gotten one of these yet, you're not doing enough free response. Go find one of these tonight. They are all over the place on the AP Chem test. They are. Thanks, guys.
Thank you.
No, Mr. Lund, I heard that we're gonna potentially be coming back for Fridays, is that true?
Possibly.
I thought they just wanted to go back to school.
This year?
No, not this year. They made like a thing, yeah, like this year, it's saying this year, but next year, like
Okay.
90.
So yeah, the next year thing they've approved. The this year thing, it might still happen. I don't know.
I don't know why they would change it, like, when you use the school day, like,
Seniors-
No, yeah, it feels like it would be kind of worthless if they tried it, but they might try it. I don't know. I got it kind of off.